Magnetic field due to a toroid. Toroid is the modified version of a solenoid. We can say if we bend a solenoid in a circular shape and join its ends, it forms a toroid. तो एक circular ring जैसा होता है toroid. In other words, a toroid is a coil of insulated wire tightly wound on a circular ring. Let us consider a toroid having n number of turns and carrying current I as shown in the figure. Now we have to find the magnetic field due to this toroid. We need to determine the magnetic field intensity at 3 points, that are P1, which is lying in the open space inside the toroid over here, P2 lying within the toroid over here, and P3 lying outside the toroid over here. These 3 points are the points at which we have to find the magnetic field. Here we assume that the thickness of toroid is very small as compared to the radii A and B. If you look here, A is the inner radius, B is the outer radius. And thickness is very small compared to the radius. That means B minus A is very small as compared to A or B. Means the toroid has large radii, inner and outer, and the thickness is very small as compared to the radii. And the turns of wire are very closely wound. So this is the assumption. To calculate the magnetic field, we have to take a sectional view of the toroid, which is shown here in this figure. This is the sectional view, side view. If you cut the toroid, it will look like this. You see these dots on the outer periphery? Those are all the, you can say, cross sections of the wire through which the current is coming outside. And the crosses which you see inside are all the cross sections of wire through which the current is going inward. So the current is going through the inner radius cross section inward into the plane of paper and coming out from the upper part of the toroid, like that. To calculate the magnetic field, we have to take a sectional view of the toroid. In simple words, it is the kind of view that we see when we cut the toroid into two halves symmetrically. From the sectional view, it is clear that due to symmetry, the magnetic field lines are circular loops which are concentric with the axis of the toroid. So magnetic field lines are circular loops which are concentric with the axis of toroid. See, this is the point or the center of the toroid through which the axis of the toroid is passing. And we consider 3 points, P1, P2 and P3, and through all these 3 points, there are 3 dotted circles drawn. Those are the magnetic field lines which are of the shape of circular loops, concentric circular loops. The magnetic field lines are in clockwise sense. Clockwise. And can you tell me why they are clockwise? All of them. What was the law or rule with which we identified the direction of magnetic field? They are saying all the magnetic field lines are in clockwise direction. Even outside and inside, all of them. All of them are clockwise. आउटवर्ड है तो फिर मैग्नेटिक फील्ड सेम कैसे हुआ? एम्पियर सर्किटल लॉ में कोएक्सियल केबल में भी याद है, यू रिमेंबर दिस, I minus I राइट हैंड थंब रूल ही है इसके डायरेक्शन को आइडेंटिफाई करने का तरीका. अब करंट in a toroid is coming out from upward, coming out. तो यहाँ पे एंटी क्लॉकवाइज होना चाहिए सेंस, लेकिन क्लॉकवाइज है. आई थिंक इट विल बिकम क्लियर एज वी गो अहेड. राइट. Now to calculate the magnetic field at the point selected, we draw Amperean loop passing through the points P1, P2 and P3 shown in the sectional view as loop 1, loop 2 and loop 3. Let us take the line integral of a general loop of radius r. So line integral of BDL is equal to B2 pi r. According to Ampere's circuital law, line integral of BDL is equal to mu naught times I enclosed. Right? B2 pi r is equal to mu naught times I enclosed. Now, each turn of the toroid passes 2 times through the area inside loop 3. Loop 3 मतलब बाहर वाला है. तो उसने बोला है कि हर एक टर्न 2 बार पास होता है, एक बार ऊपर से एक बार नीचे से. Every turn passes 2 times through the area inside loop 3. Therefore, in the area enclosed by loop 3, there are equal currents in opposite direction. Thus, the net current enclosed by loop 3 is 0. So, the magnetic field at a point outside or at the loop which is outside the toroid is 0, which is correct as per our suspicion. यहाँ पे जो arrow दिया है that doesn't make sense. Means ये जो magnetic field lines are in clockwise sense, that is general. That is not specific to the outer ring. Outer ring में तो वो cut हो जाएगा. Just like your coaxial cable. You remember coaxial cable में भी वही था. अभी हमने देखा. So magnetic field intensity along this loop is 0. Now consider point P1 lying inside the toroid. P1 lying inside the toroid. Not inside the material but inside the space, empty space. It is clear that net current enclosed by Amperean loop passing through it is 0. So the magnetic field at point P1 is also 0. वहाँ भी अंदर कोई करंट नहीं है, तो टोरॉइड के अंदर भी मैग्नेटिक फील्ड 0 होगा, बाहर भी 0 होगा क्योंकि बाहर कैंसिल हो जाएगा. Now for loop 2 passing through the point P2, the current enclosed is N times I. What is N? N is the total number of turns. And what is I? I is the amount of current through each turn. So applying Ampere's law for loop 2, we get B2 into 2 pi r is equal to mu naught times Ni, or B2 is equal to mu naught Ni by 2 pi r. Ni is the total amount of current inside or enclosed in the loop 2. Loop 2 is here. You see all these current elements through which the current is going inside, वो सारे P2 के अंदर आते हैं, और वो कितने हैं? n टोटल n टर्न्स है, और हर एक में I करंट है, इसलिए so mu naught Ni by 2 pi r. Thus it is clear from the results derived that magnetic field is zero except for the points lying in the region within the toroid. Also, for the points lying within the region of toroid, the magnetic field is non-uniform, as it is dependent on r, that is distance from the axis from the toroid. Just इसका मतलब है for the points lying within the region of the toroid, the magnetic field is non-uniform, as it is dependent on r, that is distance from the axis of the toroid, and different points in that region have different distances r. That means ये जो तुम्हें ऑरेंज वाला पार्ट दिख रहा है ना, उसमें अलग अलग पॉइंट्स होंगे अलग अलग डिस्टेंस पे, कहाँ से? एक्सिस से, इसलिए हर एक पॉइंट पे जो मैग्नेटिक फील्ड होगा वो अलग होगा, इट विल बी डिफरेंट. Yes, on that loop it will be same, but if the loop is made little bigger or smaller, the magnetic field will change. So points lying within the region of the toroid की बात कर रहे हैं, the magnetic field is non-uniform, and different points in that region will have different distance from r. That's why we can further simplify the expression for magnetic field for the points lying within the toroid. Let us assume that n is the number of turns per unit length and r is the average radius of the toroid. We can find the total number of turns by simply multiplying the average perimeter of toroid with its number of turns per unit length. So n is equal to 2 pi rn. 2 pi r is the circumference and small n is the turns per unit length. So circumference, that is total length multiplied by turns per unit length, is equal to total number of turns, that is capital N. तो वो लोग ने और सिंप्लीफाई करके इसको म्यू नॉट अपॉन 2 पाई आर इंटू 2 पाई आर एन आई, कैपिटल एन आई की जगह पे 2 पाई आर स्मॉल एन आई लिखा है. 2 पाई आर कट हो जाता है, सो म्यू नॉट एन आई, दैट्स द सेम थिंग mu naught Ni, which we got in the case of solenoid. So whether it's a solenoid or a toroid, the magnetic field, yeah, but where is the magnetic field which you are finding? That depends. This magnetic field is within the material of the toroid. ठीक है, यहाँ पे here we made a assumption that thickness of toroid is very small compared to the inner and outer radii. If this assumption is not made, then the coils of the toroid will not be circular. Rather, they will appear to be helical. For the toroid, with the helical coils, the magnetic field in the external point will be non-zero and the results derived will be different. थिकनेस ऑफ द टोरॉइड वेरी स्मॉल की वजह से ही ये जो कॉइल्स है सर्कुलर है, अदरवाइज हेलिकल होते हैं और फिर पूरा जो फॉर्मूला है वो चेंज हो जाता है. अंडरस्टैंडिंग फील्ड एनर्जी, unified concept of electromagnetic energy. Earlier, electric field and magnetic field were treated as two different forms of energy, but today it is known that both of them coexist as electromagnetic field. We don't call them separate. In certain cases or certain state, it might appear totally as electric field or magnetic field, or maybe both. The simplest example to understand may be just a point charge. When the point charge is at rest, the energy around it is only electric field energy. But when it moves, it also starts developing magnetic energy due to equivalent electric current. Electromagnetic field is manifestation of energy. We can say that energy exists in the form of electric field and magnetic field. The magnitude of energy associated with such a field can be directly related to the field intensity. If E and B denote electric and magnetic field intensities respectively in a region of space, then the corresponding energy per unit volume can be written as UE is equal to half epsilon naught E square, UB is equal to 1 by 2 mu naught into B square. So where epsilon naught is absolute permittivity of free space and mu naught is absolute permeability of free space. It is important to understand that the correct flow of information. Static electric field around a charge and static magnetic field around a static current carrying wire is like a stored form of electromagnetic energy. When either the electric field or magnetic field is changed periodically, the transfer of electromagnetic energy starts with the speed of light. After learning the concepts in this chapter, we can easily understand that periodically changing electric field always creates a magnetic field, which also changes with time. Similarly, when magnetic field changes periodically, electric field is created automatically. So दोनों interrelated है. Visualize a simple pendulum suspended freely. Suppose we suddenly provide a small amount of jerk on the pendulum so as to impart some kinetic energy to the bob. When the bob oscillates away from the vertical position, then its height against gravity increases. So its kinetic energy gets converted into gravitational potential energy. Again, the bob will swing back to the vertical position and receive kinetic energy again. Hence, whatever amount of little energy we provide to the bob initially, the energy keeps swinging the bob periodically for a fairly long period of time. But you know that there are energy losses, and so this oscillation of pendulum will not last forever. In a similar fashion, you can understand that concept of electromagnetic oscillation too. It is a natural tendency in our nature. As you try to change electric field at some location, then in response to it, one variable magnetic field is created, which in turn will generate a variable electric field and so on. Means दोनों एक दूसरे को create करते रहेंगे. जब एक yes exactly. जब एक diminish होगा तो दूसरा create होगा, जब दूसरा diminish होगा तो ये create हो जाएगा वापस. So any change in EM waves में है, EM waves में ये part. For now, it is not important to know how to generate oscillating electric or magnetic field, but you have to understand this fact that very well that whenever you generate an oscillating electric or magnetic field, then in any case the other field is automatically created to transfer electromagnetic energy with the speed of light in the space. This phenomena of transfer of electromagnetic energy is called electromagnetic waves, of course, EM waves. Example of source of electromagnetic waves. When a charged particle oscillates, it generates electromagnetic waves in its surrounding. This is because when charge oscillates, the electric field in its surrounding space changes periodically everywhere due to periodic change in its position, and hence there must be dissipation of energy in the form of electromagnetic waves. मतलब electromagnetic waves are the dissipated energy which are emitted at the speed of light due to the change in electric or magnetic field. Yes, yes, exactly. So consider an iron block. We know that iron nuclei are connected together at regular separation with the help of outer orbit electrons. Due to increase in temperature, these iron nuclei continuously oscillate. Since there is net positive charge in the nucleus, it must be dissipating energy in the form of electromagnetic waves. In fact, in a steady state condition with the surrounding space, these iron nuclei will be absorbing thermal energy at a particular rate, and it also will be dissipating with the same rate in an electromagnetic form. and the chapter is over. But before I complete it, I would like to go to Biot Savart and just discuss that small part. Yes, exactly. ओके तो यहाँ पे हम लोग थोड़ा सा कंफ्यूज हुए थे कि हाउ दीज एंगल्स आर थीटा एंड 90 एंड व्हाट नॉट, जिससे हमने ये डेरिवेशन किया था. ओके सो यू सी दिस पॉइंट ओवर हियर, यहाँ से करंट बाहर की तरफ आ रहा है, करंट इज कमिंग आउट. यहाँ से करंट अंदर की तरफ जा रहा है. दिस इज द 3D इमेज. ठीक है, सो दिस इज योर करंट एलिमेंट. करंट इज कमिंग आउटवर्ड परपेंडिकुलर टू द प्लेन ऑफ पेपर. ठीक है, वी हैव टू फाइंड द मैग्नेटिक फील्ड एट पॉइंट P. Now the magnetic field at point P will be perpendicular to the position vector connecting the current element and the point P at which we are finding the magnetic field. So position vector क्या है? R. अब R और dB सेम प्लेन में होंगे. हाँ सेम प्लेन में होंगे बट एक दूसरे से परपेंडिकुलर होंगे. हाँ, और ये दोनों से परपेंडिकुलर होगा तुम्हारा करंट एलिमेंट. मतलब जनरली ये तीनों एक दूसरे से परपेंडिकुलर होते हैं, करंट एलिमेंट आर और बी. तो यहां करंट एलिमेंट और आर तो परपेंडिकुलर है डेफिनेटली. क्यों? क्योंकि ये इन द प्लेन ऑफ पेपर है और ये परपेंडिकुलर टू द प्लेन ऑफ पेपर है. ठीक है, तो उनके बीच का एंगल तो 90 हो गया. बट व्हाट अबाउट मैग्नेटिक फील्ड? वो किससे परपेंडिकुलर होगा? दैट विल बी परपेंडिकुलर टू द करंट एलिमेंट डेफिनेटली, because it's perpendicular to the plane of paper, so it has to be, dB has to be in the plane of paper, but it will also be perpendicular to the position vector, that is r. मतलब ये एंगल तुम्हारा कितना हो गया? 90. ठीक है, now we know that this is 90. Do we know this is 90? Yes, absolutely. ठीक है, and this is theta. ठीक है, so how much will this angle be? 90 minus theta. Now we know that this is 90 यहां से यहां तक, और ये 90 माइनस थीटा है, तो ये कितना होगा? हाँ, तो सिमिलरली अगर ये थीटा है तो वी कैन फाइंड द रेस्ट ऑफ द एंगल्स. ये थीटा है तो ये डी बी कॉस थीटा होगा बिकॉज ये डी बी है, और ये डी बी साइन थीटा होगा. Similarly, this will be theta by the same idea. See, this is dB, which is making 90 with the position vector over here, and this is 90 because we know it. Why? This is theta, so this will also be theta. तो ऐसे करके सारे एंगल ढूंढे. यहाँ पे लिखा था ना, let us consider only the top segment which is directed outward and perpendicular to the plane of paper. The position vector of the point P with respect to this segment is on the plane of paper. Hence, the angle between current element vector and position vector is 90 degree. Makes sense now? And फिर वो लोग ने dB निकाला था. फिर तो कोई टेंशन नहीं है, वो मतलब डायग्राम से हम लोग ये पूरा स्टडी कर सकते हैं. Yeah, but there are lots of formulae which you need to keep in mind and note down. नहीं है, इनिशियल में ही है. इनिशियल इलेक्ट्रोस्टैटिक और मैग्नेटिज्म बहुत ज़्यादा लेंदी है, बहुत ज़्यादा फॉर्मूला है. बट देन इट इज़ क्वाइट थियोरेटिकल ज़्यादा है, थियोरी ज़्यादा है उसमें. ठीक है, मैं वीडियो पॉज कर रहा हूँ, मतलब स्टॉप कर रहा हूँ. तुम ये फॉर्मूले सारे नोट कर लो.